So when there are two charges, say point charges, and there is some force between them, and say one charge changes its location, then how quickly the new force establishes, how does the other charge know about the changed position? To solve all these problems, we have a concept called electric field, which makes us think in a different way. Here we are thinking that Q1 is applying force on Q2, Q2 is applying force on Q1. That's it. We are thinking about just Q1 and Q2. But when we think about electric field concept, then it is like Q1 creating some environment around itself, not just close to itself, but even farther away from itself. Likewise, the other charge, both charges creating some environment due to their presence. If Q2 is there or not, Q1 will create this environment, whether Q2 is there or not there. Whether Q1 is there or not there, Q2 will create this environment. Now, when we start thinking like that, then we are able to solve this problem, that what if Q2 is moved? How does Q1 know that Q2 has moved? How does Q1 know that it has to apply a different force, different magnitude and different direction? How quickly that new force will be applicable? We can handle all those questions now without any problem. The field was there. It was there everywhere. Q2 where is placed right now. There some field is there due to Q1. If Q2 goes to some new position, even in that position, at this moment of time, when Q1 is not there in the new position, even at this point of time, there is field at that point due to Q1. So when Q2 is moved to that new position, field was there earlier, it is there now also. So immediately, force can act. So it's not like Q1 is searching for Q2. Q1 is just creating a field everywhere due to its own presence. That field is not visible to us, but it is there. And a charge can detect that field. Just like a mass can detect gravitational field, a charge can detect electric field. But you don't need the presence of charge Q2 for the electric field due to Q1. Now, because it is something that we don't see, it is difficult to visualize it. So a concept of field lines is developed so that it helps us to visualize. There are no field lines in reality. No lines exist in space. Though electric field can be everywhere, you don't have any lines in space. So they don't exist. We have created them so that we could visualize the electric field. And we have made some rules about those field lines. Say, if the lines are closer, then it would mean that the field is strong, and if two lines cannot cut, then arrow must show the direction of the field. Arrow must show the direction of the field. Now why can't they cut? Because if arrow is showing the direction of the field, then cutting means at the point of intersection you can have two different directions for the field. But two different directions for the field, how can that be possible? Now, I just tried to give you a picture, so to say, of the concept of electric field. There is bound to be some mathematical definition of electric field. So what is the mathematical definition of electric field? Suppose we want electric field due to Q1. Place any charge, Q2 if you like, or any test charge where you want to know the field. Please note that field can be different at different points. Field can be uniform also, but it can be different also at different points. Say you want field at a particular point. Place a test charge there. See how much force that test charge is experiencing. Divide that force by the test charge. Divide that force by the test charge. And take that test charge to be positive charge. I repeat, to know the field at a particular point, place a test charge there. Let it be positive. Find out the force, vector F, acting on that charge. Divide that vector F by that test charge Q, whatever Q or Q2. That is the definition of electric field at that particular point. That electric field could be due to Q1. But why just Q1? Sometimes we may want to know the field due to a cluster of charges, maybe 100 charges, jointly creating field at a particular point. Just like 100 charges can apply force on Q2. So there can be field due to 100 charges. So we have a pictorial view of electric field concept, and we have a mathematical definition of electric field concept. Now, what is the direction of the electric field? What is the direction of electric field? Let's visualize Q1 and Q2. Let Q2 be the test charge. Let it be positive. Right? So Q2 will experience force in certain direction. Q2 will experience force in certain direction. And you are dividing that force by Q2. But Q2 is positive. You are dividing a vector F by a positive number. Q2 is a positive number. When you divide a vector by a positive number, you don't change its direction. So direction is the same as for the force. That a positive charge would feel at that location. So Q2 is a positive charge. In whichever direction it is experiencing force, the field due to Q1 will be in the same direction. And I'm just trying to simplify by saying Q1. There can be a cluster of charges, and we may be interested to know field due to the cluster of charges at Q2. And sometimes it doesn't have to be a cluster of charges also. It can be a system, a uniform system like a solid ball or a solid cylindrical shape, any shape. So you can always talk about field due to such shapes at a particular point. So at that particular point you will place Q2 or a test charge which is positive. See what is vector F there. Divide that vector F by the test charge. So force divided by the test charge. Now if I am talking about point charge, Q1 case. If I am talking about point charge, field due to a point charge, in that case I can use Coulomb's law. Now that's a very important statement, by the way. I have seen students applying Coulomb's law the wrong way also. Say for example you have got two cylinders. Both cylinders are charged. What is the force between these two cylinders that are charged? The answer is not K product of charges divided by distance square. It is going to be a very complicated problem to handle, because Coulomb's law works for point charges, spherical symmetries, solid or shell like spherical symmetries. So the moment you are using the formula K Q1 Q2 by R square, then you are not dealing with any shape. You are restricting to certain shapes, point charges or uniform spherical charge distributions. Let's assume that Q2 is a point charge. Then force F is given by Q1 K Q1 Q2 divided by R square. K Q1 Q2 divided by R square. And that force we are dividing by Q2. So K Q1 Q2 by R square whole divided by Q2. So Q2 will cancel out and you are left with K Q1 divided by R square. This is the formula for electric field due to a point charge Q1. Let's make it Q now. So it would be K Q by R square. That's the standard result, very useful result, very easy to remember because it has come directly from Coulomb's law. And since I said that Coulomb's law is fine if you also have spherical symmetries, this result would be valid. KQ by R square result would be valid if small q is point charge, it is a spherical symmetry. Spherical symmetry. Any questions up to this point? Let me know. All right, let's talk about something like hydrogen atom. There is field due to proton, due to the nucleus, and electron is at certain distance, say 10 to the power minus 10 meters. What is the electric field at that distance due to proton? It will be as simple as KQ by R square, where Q is 1.6 into 10 to the power minus 19 and R is 10 to the power minus 10 meters. Can you tell me what would be the direction of the electric field at this point? Right, left,
right,
up, down, whatever. Correct.
right.
Right is correct. Yes. And suppose we consider an electron here. In which direction would it experience force?
Sir, left.
Towards the positive. Left.
Left. Left. So electron will experience force in the left direction. What is the unit of electric field? Electric field is force upon charge. So Newton per Coulomb would be the SI unit. All right. Now try this question. You can see two charges, plus minus. Due to them together, what is the field at B? When there are multiple charges, how does one find field net at a particular point? Electric field is force vector upon charge. Since force is a vector, electric field is also a vector. So you need to add the two vectors, E1 vector plus E2 vector, due to the positive and negative charges, to find the resultant field. Yes.
Sir, left.
Left. I think I need to say one more thing. Let their magnitudes be equal. Positive and negative charges, let their magnitudes be equal. So let's say one is plus Q, other one is minus Q. Why would it be left? Isn't minus charge closer to B? Put a test charge at B. Put a test charge at B. Positive charge. Will the repulsion be more due to the positive charge, or will the attraction be more due to the negative charge?
Sir, attraction will be
more due to the negative charge. Attraction will be more.
Yes. So that means net force will be in which direction? Left or right?
Net right. Right side.
Now how is it right now? If left side force is more, attraction is more, right? So if left side is more, left side force is more, net force will be on the left side, isn't it? Net force divided by charge, positive charge. That is the direction of field. So what is the answer?
Left.
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 Any questions? Let me know. All right. Okay, you can also see it on the board, what I tried to draw. Right side arrow you will see is smaller, left side arrow you will see is larger. That means net force is on the left side. So if you put a positive test charge there, it will be pulled towards the left side. That's the direction of the field. Alright, here comes the next one. One charge is plus Q, other charge is minus Q. So what happens at C? Is it 0? Right, let's see. If I put a test charge at C, 0. If I put a test charge at C, okay, let's discuss now. So putting a test charge at C, repulsion will be, blue is positive, repulsion will be towards right side. Right? But minus will attract. Why would they cancel? They won't cancel. So due to the blue charge, right. Due to the red charge, also right. So the net force is going to be on the right side. So what's the answer?
The right.
Right side. Net force upon positive charge. Right side. Now you can see those arrows also. Both are on the right side. All right. Now, what is the difference between force and field? Well, force acts on a charge. Force acts on a charge. And that charge is located at some point. Field does not need the presence of any charge to experience. Force, a charge has to experience. Field can still be there and charges are not there to experience the field. That's very much possible. Both are vectors. That is a similarity. If you know the field at a particular point, then if a charge is placed at that point, force acting on that charge will be QE. I hope this is clear. If you know field at a particular point, at that point charge Q will experience QE force. And it is a vector equation. If Q has got negative sign, then vector F and vector E will be opposite. If Q has got negative sign, then vector F and vector E will be opposite. If Q has got positive sign, then vector F and vector E will be in the same direction. That is why I was talking about positive test charge. Positive test charge. Because if I keep the charge positive, then vector F and vector E are in the same direction. But if I keep the test charge negative, then they become in opposite direction. Remember that hydrogen atom type of example that we discussed, the proton having electric field on the right side. But if electron is there on the right side, even though the field is on the right side, electron will feel leftward attractive force. So proton, right side of it is electron. Electron is attracted towards proton, left side force it experiences. But the direction of field due to the proton is towards the right side. So direction of the field is determined by placing a positive test charge. If there is a negative charge, then that negative charge would experience force in the opposite direction to the field. Any questions? Let me know. All right. Now, I already mentioned this point when you were doing one question. There were two charges, plus and minus. If you want to know field due to two charges at a point, then vector E1 due to one charge, vector E2 due to the second charge, add the two vectors. As simple as that. It is more of vectors rather than electrostatics. Electrostatics part is up to finding E1 and E2. After finding E1 and E2, doing the vector addition has to do with vectors. It is just like there is a particle on which several forces are acting: gravitational, normal reaction, friction. And you want to know the total force on that particle. So what would you do? You would add vectorially: gravitational force, reaction force, whatever, frictional force, all of them. F1 plus F2 plus F3, all vector. Here it would be E1 plus E2, and if third charge is there, E3, fourth charge is there, E4, E5, E6, E7, E8. It will just go on and on like that. Now, try this one at A.
Sir, it's towards right. Right.
Towards right. Let's see. Yes. Towards right should be correct. Now, put a test charge positive at A mentally, so that the blue fellow will repel it as shown. The red fellow will attract it as shown. Two vectors, you have to find their sum. By symmetry, it can be easily seen that it would be on the right side. So net force is on the right side. Force divided by positive charge. Field will be in the same direction. You are done. Any questions? Let me know. Yes, carry on.
Test charge always have to be positive.
It is always convenient to take it as positive. It is always convenient to take it as positive. We can put negative charge. It will increase the complication little bit. Once you have enough experience, you can do that. But at least right now, take it as positive. Yes, any other question?
Thanks, sir.
All right, then here comes next question. Now we have got both positive.
Sir, up.
At point A.
Sir, up.
Up.
Sir, upwards.
All right, let's see. I think it is correct. All right, so let's put a test charge positive at A. Repulsion due to the left fellow. Repulsion due to the right fellow. Vector sum by argument of symmetry will be up. And therefore field will be up since we are placing positive test charge. Done. Now, earlier I was saying that because we don't see field lines, they don't exist actually. It is difficult to visualize. So we have a concept of field lines. They give us an overall picture. They give us an overall picture. Imagine you are analyzing field due to a positive charge, a field due to positive charge. Well, field due to positive charge where? You are trying to visualize at several points. Several points. One point is shown on the board right now. And look at another point. It is closer, so you can see that big vector. Closer means field will be larger. And if you look at a third point, it is farther, so the field is smaller. And likewise, so many points we can consider. So when we try to analyze the pattern at various points, then this type of approach may not give us an overall view. Just an overall picture it may not give us, looking at various points. And this field lines concept does give us a nice overview for a particular charge at various locations. It gives us a nice overview of the whole situation. Like you must have seen the magnetic field lines due to a magnet, bar magnet for example. Somewhat like that type of concept we have here also. But in bar magnet, you will always see that field lines would close. Yes, in especially lower classes, they may not tell you that magnetic field line actually goes through the magnet inside it. Magnetic field line is close. But in case of what we are discussing right now, electric field lines don't close. Magnetic field lines close, but electric field lines don't close, that we are discussing right now. Later on, when we discuss magnetism, then you will see that there can be another type of electric field. And for that electric field, field lines are like magnetic field lines, closed field lines. So electric field that we are discussing right now we are discussing electrostatics, where charges are not supposed to be moving. The moment charges start moving, then another thing happens, and that's where another type of electric field can come into effect, for which it can be a closed line, like magnetic field line, which is closed. But right now we are talking about electrostatics, and in magnetism, why you have a closed field line? Because you don't have two poles that can be isolated. You don't have two poles that can be isolated from each other. They are like one unit, both of them. So in magnetism, you don't have plus charge, minus charge separated, north pole, south pole separated. If that had been the case, then in magnetism also you would have had non-closed field lines. If north pole could be separated from south pole, magnetic field lines would have looked different. But they don't. They don't start and close. They actually are round and round, because north pole and south pole are not separable. But here positive and negative charges are separable, and that's the reason why electric field starts from one point and ends at another point, right? So that closed type of behavior you don't see in electric field in electrostatics. So the problem is that we want to get a bird's eye view of electric field at various points for this type of charge, positive charge, let's say. And this way it is not working for us. Now, we introduce some imaginary lines called electric field lines. And we say that their density would mean the field is strong in that region. Density means closeness, their closeness. And we say that arrow will tell the direction. So we may not be interested in the exact number. As I said, bird's eye view. We want to get an overall idea. That's it. Not exact number at a point. So closeness of field lines would mean that field is strong there, and direction, arrow will tell us the direction. And one more thing. I can have many charges also. So if there are many charges, then if charge is higher, say 8 coulomb charge versus 4 coulomb charge, then we will show double field lines from 8 coulomb charge in comparison to 4 coulomb charge. So we follow certain convention. Number of field lines would be proportional to the strength of the charge. Closeness of field lines would mean strong field in that region. And if the field lines are farther away from each other, it means that in that region field is diluted or weak, then arrow giving us the direction at a particular point. Now you can understand why two field lines would never intersect each other. How can at one point you have two directions of electric field at the same point, which is the point of intersection? Right? So they would never intersect, two field lines. Now that's true for gravitation or magnetism or electricity. Now look at that. Just look at small value of R near the charge. Near the charge you will find they are close. Near the charge. You can imagine a circle, very small circle. Field lines are very close. But if you draw a big circle, you will find that field lines are far apart. Big circle means large distance we are trying to imagine. Large distance, big circle. So the density of field lines is becoming lower for the large circle. So that is that's the field lines. These are the field lines for a positive charge. Why positive charge? Because they are going out. They are going out. If you put a positive test charge and you are discussing positive charge, then repulsion should take place. So field lines would always go away from the positive charge. Had there been negative charge there, and then if you put a positive test charge, imagine negative charge there, and imagine positive test charge, test charge would be attracted. So the direction would be exactly opposite to what is shown here. So if you have got a negative charge, then field lines will go into it, negative charge. Positive charge, field lines will go away from it. Right? So some synergy with North Pole, South Pole type of concept, some synergy. But the difference is that positive and negative charges can be isolated from each other. If I make an electric dipole, imagine just like bar magnet, we create an electrical analog, a positive negative system. You have seen those systems in chemistry, chemical bonding, dipole, where we discuss the dipole concept, where we discuss the dipole moment concept, plus and minus charges separated by some distance. That is going to be just like a magnet, bar magnet. I mean the field lines of that plus minus system is going to be just like the field lines of bar magnet. But because plus and minus charges they can be isolated from each other, and that is why that closeness type of thing is not there in case of electric fields. Yes, any questions? Let me know. Now, this is for you to try out.
Sir, positive.
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 So positive.
Yes.
Positive.
Going out means A has to be positive. Going out from A. Compare the ratio of charges QA to QB. Number of lines is proportional to charge. Use that concept. From A, how many lines are shown from A?
Sir, 8.
8. And B?
4.
4.
4.
That means
Sir, QA
A
is equal
should
to
be
2 QB. Is equal to 2 QB.
correct.
Sir, third.
Third one. That should be the correct answer. Third one. So that's the convention we follow, right? When we draw this type of thing, we follow that convention. We don't arbitrarily draw as many number of lines as we please. Yes, any questions? Let me know. All right. You agree or disagree? X greater than Y. See closeness of lines. Take two lines. See how close they are near X, how close they are near Y.
So false. It's false. False.
False. Near X, if you take two lines, they are really far away. Near Y, they are quite close. So at Y, field should be stronger. Density of field lines gives E. Yes, any questions? Let me know. All right. You can see some field lines and you don't have to answer it right now. This is your assignment question. We stop now.